Good morning, everybody. We are beginning a study of what is called oblique triangles. Now, what is an oblique triangle? An oblique triangle is a triangle that does not have a right angle. This means these triangles could be either acute, where all the angles are less than 90 degrees, or they could be an obtuse triangle where one of the angles is greater than 90 degrees. Now, to solve an oblique triangle means that what you're going to do is you're going to find the links, the missing links and the missing sides, all the measurements of those. All right? So there are four cases that we're going to solve over the next few days. Four cases. And those cases sort of have familiar names from geometry. They are the angle, side angle, or angle, angle, side case, which is the case where you know two angles and a side. Okay? And then the case where you have two sides and an angle. Two sides and an angle that you know. And then two sides and the, if you'll remember from geometry, the included angle. All right. And then finally, the last one is knowing all three sides. Okay. Now, just so you know, these two we will talk about tomorrow. They are done by the law of cosines. Okay. These first three are done by the law of sines. And I'm going to circle this one in red, side angle. If you spell it backwards, yep, spells a bad word, right? Okay, so there's the joke for the day. But in all seriousness, if yours spells a bad word, then that means that this case is trouble. All right? In fact, it's called the ambiguous case, and it has three separate situations. So this is not really a joke. It means that I actually always write it this way because when I do that, that's like a clue. Oh, okay, this one's trouble. I need to think about it more because I got to figure out which of the three separate situations I'm in. Okay? And we'll talk about that in a minute. That'll be the last thing we do today. So we're going to do the law of sines, and what we want to know is where does the law of sines come from? Okay? The law of sines comes from this situation. If you take a triangle, okay, and we have three angles, angle A, B, and C, and we just draw an altitude, let's say to make a right angle. Remember, an altitude is from one vertex perpendicular to the opposite side. Well, if we do that, then these other sides, a little b, little c, and the altitude we'll call h, the height, okay? If we look at this, then we can create like little sine ratios. So I can say like the sine of angle A is equal to h over the hypotenuse, h over b. All right? But I could also say the sine of angle B is equal to h over a. And what we notice is that both of these have an h. So we could solve for h in each case. And so we get h equals b sine a. And we get h equals a sine b. All right. Now, since they're both equal to h, we can set them equal to each other. B sine a equals a sine b. And we're going to divide this side by b, so this side by b, and we'll divide the right side by a and this side by a. And so what we end up with is this right here. Sine of angle A over side A, which is the side opposite angle A in the oblique triangle, is equal to the sine of angle B over B. Now, if you decide that you want to draw some other altitudes and do this again, then you're going to find the other ratio, sine C over C, is equal to one of these. And so this creates, and I'm not going to do that one, it works just like this one. This creates what we call the law of sines, okay? These three ratios are all equal to each other. And so what it means is that because we can draw an altitude in any triangle, if we know, a couple sides and a couple angles of a triangle, then we can find the missing sides, and we can use the law of sines to do that. And the cases, again, that it works on, it works really well on the cases where you know two angles, angle side angle and angle side, but it also works on the case, the ambiguous case, angle side. Now books always write it as side angle, and again I always write it this way because it tells me, okay, this one's trouble. All right, and so that's and I do that on purpose, and that's always helped me to remember to watch out. So just so you know, keep that in mind. All right, here we go. Let's do some examples now that we know where it comes from. So here's our first triangle, and we want to look at this. I always like to draw a picture of it, so I know two angles. So what I do is I just draw a picture. Here's angle A, it's 40. Angle B is 50. Side A is 4, okay? And then there's angle C. So the first thing I can always do is find angle C. So if I take 180 degrees minus angle A minus angle B, sorry, angle B is 60, not 50. I apologize. Minus angle B, then I get 80 degrees for angle C. Okay? Now, this is an oblique triangle. It's acute because all the angles are less than 90. And doing that helps me anyway. Setting this all up gives me all the information I need. Now, the directions are always solve the triangle. Solve the triangle. Okay? And that means in this triangle, I found the measure of angle C, okay? So I need to find side C and side B. Those are the things I need to find. So I'm going to use the law of sines. So I'm going to take the sine of angle A, which is 40, and divide it by 4, which is side A, and that will equal the sine of 80 angle C over C. And then I'm also going to take the sine of 40 over 4, and that's equal to the sine of 60 over B. So I have two equations here that I can now solve. All right? And so I can do some cross multiplication and division to get what I want. So on this side, I get C sine 40 equals 4 sine of 80. And then that is C equals 4 times the sine of 80 divided by the sine of 40. So now that I have all that, I can punch it in a calculator. Okay? And I'm doing that right now. I'm punching it in my calculator. Oh, by the way, these are degree measures. So when doing the law of sines, make sure, remember what I said, make sure your calculator is in the right mode. So put it in degree mode. Okay? So now we've been using radian mode a lot. Now we got to switch to degree mode. So 4 sine of 80, make sure I put that 80 in parentheses, and then I divide by the sine of 40. All right? And I end up with C is equal to 6.1283 dot, dot, dot. It goes on forever. So they're going to tell you to round it off to either the nearest tenth or the nearest hundredth. So your answer will be 6.1 or 6.13, depending upon what you were asked to round to. Okay? Either one. So make sure you do that. All right, let's go and do the next one. So I do the same thing, B sine of 40 equals the sine of 60 times 4. And then I divide both sides by the sine of 40. So B equals 4 times the sine of 60 over the sine of 40. And then I go ahead and work that out on my calculator. I'm in degree mode, and I get B equals 5.4 or 5.39, depending upon what they asked me to round it to. Okay, so make sure you round correctly and give the correct rounding based on what they say. Now notice these are really approximations, okay? And so you want to keep that in mind as well. Other than that, you can see these side lengths match up because I got a side of 4 and now I got a side of 6 and I got a side of 5, and the longer side is opposite the bigger angle. So all our theorems of geometry are being satisfied here. Okay? So that's the first example. Now, when I drew this out, just so you know, this was an angle, and a side. So this was the angle side case. And this is very typical. It's very easy. All right? Okay, so here's the next problem. We have A is 35, B 15, C equals 5. And we would do essentially the same thing. 180 minus 15 minus 35 is equal to 130 degrees, which is the measure of angle C. So we know that's now 130. All right. And now it's basically an angle side situation, even though we started off and this was as an angle side angle. So angle side and angle side angle are basically the same situation. You do the problems essentially the same way. So we know the side opposite angle C, so we can do sine of C over C is equal to the sine of A over A, and that'll help us find A. And then we can do the sine of C over C equals the sine of B over B. And so now, and that'll help us find B. So now I'm just going to work through these. And so magically, you can see that this is complete. And when I have found A is equal to that and B is equal to that, I've rounded to 2 and 1 decimal places. So make sure you try this one yourself and check your work. All right, there's the whole problem. Okay, so that should help you. You can pause the video if you want to take notes on this and work through it. Okay, let's go to the next slide. So I have given you 3 situations here, okay? And when you go to solve for triangles, okay, you can end up with various things happening. Now, these are examples of the infamous side-side angle, or as I said, the bad word that tells me something's going on. And so typically you'll be giving 2 sides and an angle, and then the first thing I would do is draw these out, okay? So for instance, if I was looking at this first case, A equals 3, B equals 2, angle A is 40 degrees, then whenever I draw these out, I always draw the angle first. So there's 40 degrees, okay? And this is angle A. And then angle B is going to be over here, all right? And so side B is going to be 2, and side A is going to be 3, okay? Now, if you look at this one, that with a side of 3, we're going to easily reach this side over here, okay, and create an angle B. And then that 3, we could also, it's longer than the other side, right? So you could swing it over here, but then it goes too far, you see that? So it doesn't create a triangle there, all right? Because it swings too far to touch it. So in this case, since we can't swing it because it's longer than that side, okay? That means the 3 is too long. This is a 1 triangle case, okay? So let's look at the next one. So the next one, same thing. We draw angle A. Now, angle A is 35 degrees, okay? And again, we know side A is over here, and it's equal to 6. But side B is equal to 8, okay? So now let's look at it. Here's side B. Angle B will be over here now. In this case, we could swing this side over and end up making a completely different triangle. So one of the oblique triangles is acute, but the other one could end up being obtuse. And so this is what's called the two triangle case. All right. Now notice, in this first one, the given side of A is longer than the given side of B. In the second one, the given side of A is shorter than the given side of B. Okay? But A is long enough to swing over and touch. That's a two triangle case. So let's look at the third situation. So A is 2, B is 1, C is 50. Okay? So now I draw the angle first. That's 50 degrees. Okay? And so this is going to be angle A over here. All right? And angle B will be up here. And now A is 2, and then the B is only 1. Okay? And it turns out the angle is big enough that the B can't reach. It's not long enough. Okay? Now you won't necessarily be able to tell this for sure with a diagram. And so I'm going to give you something that'll help you check whether the B values are long enough or not long enough. So this is the no triangle case. No triangle can be made from side lengths of those. All right? And then finally, there is another one triangle case. And so in this case, what happens, let's say it's angle A and it's 40 degrees, and they give you 2 here. What happens if B is just the right length to reach? Well, then it makes a right triangle. Okay? Or side A is just long enough to reach. So you could make one right triangle. All right? And so it's this case that'll give us a test that we can use to help us with these other two cases. Okay? And to know for sure which one is right. So what would the test be? Well, we know the sine of 40 would equal A over 2. So if we get sine of the given angle is equal to the opposite over the hypotenuse, if this is true, okay, then we have a right triangle. If when you do the opposite over the hypotenuse, if it's too small, like in this case, you have like 1 over 2 is smaller than the sine of 50, then that means that you have a no triangle case. And in this case, you get 3 over 2, which is bigger than the sine of 50, then that means that you're going to have a one triangle case where it's one oblique triangle instead of one right triangle. So you're looking for greater than, equal to, or less than. And the greater than, equal to are one triangle cases. Equals is the right triangle case. And the less than case is the no triangle case. So that's everything that you need to know. Now this is all in your text, and you might want to read through this again. And all I've done is talk through it, and now I'm going to show you. Okay? So I have written out what you need to do these problems. I draw the triangle, I put the 40 into the angle A, I put B is 2 and side A is 3. Now, I draw H here. H is the altitude. It makes a right triangle. So I know the sine of 40 is equal to H over 2. Now, why is this important? Because I can compare A to H, basically. So 2 times the sine of 40 is equal to H, right here, 1.29. And I can see that A is bigger than that. All right? Since A is bigger than the 1.29, it's big enough to reach side C. However, 3 is also bigger than side B, so that means there's only one oblique triangle. Okay? So it's actually too big to make two triangles because it would rotate over and it'd be too big. Okay? So that's the idea. That's how you check. You've got to do this think about to do law of sines. So now, once I've got that all set up, I can set up the law of sines to solve this. I know there's only one triangle, so I can do sine A over A is equal to sine B over B, okay? And that gives me then the sine of 40 over 3 equals to the sine of B over 2. So notice here we're not solving for a side, we're actually solving for an angle. So I can multiply both sides by 2 and I get 2 sine 40 divided by 3 equals the sine of B. Okay? Now, to solve for B, I need to take the inverse sine of both sides. So the inverse sine of 2 sine 40 divided by 3 is equal to angle B. All right? I'll put that here so we can fit it in. All right? And that's what I'm putting in my calculator. Now, I want you to know you probably have to put parentheses around the 40, okay? But everything should work. So I'm going to do this. So I go second sine inverse, and then I have a parenthesis, so I do 2 sine 40, close that parenthesis, 2 parentheses, whoops. The sine 40 on the inside, I have to divide by 3, and then I close the parentheses, and that should be everything. Enter, and I get that 25.4 or 25.37, depending upon what they make you round to, is equal to angle B. So these are in degrees. So 25.4 degrees or 25.37 degrees. Now I know 2 degrees, right? I know 40 degrees and 25 degrees. So this is one of the things I needed to solve for. All right. So now I take 180 minus 40 minus 25.4. Okay. I get 180 minus 40 minus 25.4. And that's equal to 114.6 degrees, which is angle C. Once I have angle C, then I can do sine of A over A equals the sine of C over C. And I can solve for side C. So the sine of 40 over 3 equals the sine of 114.6 over side C. Okay? And that means C is equal to 3 sine 114.6 over sine of 40. And that should give me side C when I calculate it. 3 sine 114.6 divided by the sine of 40. Now, make sure you round things off to whatever they tell you, okay? And so side C will be 4.24. And that makes sense. I have a triangle with a 2 and a 3 side and now a 4.2 side. So there's my last answer. So I've now solved the triangle, found angle B, angle C, and side C. Okay? That's one ambiguous case. So let's go ahead and do another one. Okay, let's play the game with this one. I've got everything written on the board, so you might want to pause, write these notes down, and then listen to me talk through it. So here's how it works. Here's the original stuff we were given, okay? The original stuff we were given is right here. A is 6, B is 8, A is 35. Now, like always, I draw the angle first, okay? Then I put side A opposite, and then side B. Then I drew in the altitude, right? Because I got to compare to that altitude. If I'm smaller, I make no triangles. If I'm exactly equal, I make a right triangle. If I'm big enough but smaller than the other side, I make 2 triangles. If I'm big enough but bigger than the other side, I make 1 triangle. So what happens in this case? I take h over 8, opposite over hypotenuse is sine of 35 in the right triangle I've drawn in there. So h is 8 times sine of 35, so h is 4.59 length, which is smaller than 6, which means a side of length 6 is big enough to reach side C, right? But if you look over here on the right, I've redrawn the triangle, and that side, A equals 6, follow the yellow line, it can swing over and actually touch side C in 2 sides. So the red triangle with angle C smaller and side C smaller is 1 triangle, and the white triangle with angle C bigger and side C bigger is the other triangle. This is the 2 triangle case. Now we're going to solve for both of those triangles, okay? Now, the goal is do the white one first, okay? Do the white triangle first. So I'm going to shrink this so that we have this available and I can refer to the diagram. But we're going to do the white triangle first, so ignore the red markings at this point. Basically, we have everything we need, and so we can go sine of A over side A equals sine of B over side B. So that gives us the sine of 35 over 6 equals the sine of B over 8. And so that makes this 8 sine 35 over 6 equals sine B. And just to move it up just a titch, that means the inverse sine of 8 times sine of 35 divided by 6, close parenthesis, equals angle B. So that is going to equal, and I'm going to calculate that on my calculator, So I press inverse sine, and then I go 8 sine 35, close parenthesis, divide by 6, close parenthesis, enter. I get 49.9 degrees, okay? So I'm going to round to 1 decimal. So that is one thing. I have now found B, okay? So then I can move up here, all right? And we're going to keep working, all right? And we then do 180 minus 49.9 minus 35, and that will equal angle C. All right, so 180 minus 49.9 minus 35 equals 95.1. All right, so that's angle C. That's the big angle C in the diagram. I just marked it in the diagram. It's the big angle C. Okay? And so now we can do sine A over A equals sine of angle C over C. And so that's the sine of 35 over 6 equals the sine of 95.1 over C. So C equals 6 sine 95.1 divided by the sine of 35. All right, so I figure that out. 6 sine 95.1, close parenthesis, divided by sine 35. And that is equal, C is equal to 10.42 or 10.4 units, however long it is. So there's C and there's angle C. I could put a degree symbol on that. And there's my first triangle. Okay? First triangle. Now, the important thing in this first triangle that I need to do the rest of the problem is this right here. It's the angle on the bottom, okay? So I'm going to show you why right now. Why is that important? So we're going to blow this up again. The angle on the bottom was 49.9 degrees. Notice this side is A equals 6, and this side is A equals 6. That means the triangle with the two A equals 6 sides is isosceles. That means this angle is 49.9. So the new angle B, which is right here, is supplementary to the old angle B. So if we take 180 minus 49.9, the new angle B is 130.1. This is how you do the two triangle case. Use the isosceles triangle facts to help you find the new angle B at 130.1. Okay? So now that I know that, now I'm going to do the next case. All right. Okay, now that we have that 130.1 degree angle, let's go ahead and write that down. B equals 130.1 degrees. Now, when I was in school, because I was writing all this in the same color, I would call it B prime for the second angle B for the next triangle. So I found angle B for the first one. Here I have colors, but that's kind of how I distinguished them. All right. Now, so since now we have two angles in that triangle, we can find angle C, the skinny triangle in that one, which is this angle right here, the skinny angle C. Okay, so we're going to find that. And we can just do that by doing 180 minus 130.1 minus the 35 degrees, which will give us 14.9 degrees. And that will equal C prime. Okay? Once I have that, I just have one law of sines to do. I can do sine angle A over A equals the sine of angle C prime over little c prime, if you wish. So that'll be the sine of 35 over 6 equals the sine of 14.9 degrees over little c prime. And little c prime will equal 6 times the sine of 14.9 over the sine of 35. And that will equal, calculating on my calculator, 6 times sine 14.9 divided by sine 35. And that's equal to about 2.7 or 2.69, depending what they want you to round it to. And so that is the last thing we had to find. Okay? And so we have now solved for two triangles based on the swinging hinge. All right? So again, make sure you do what's in the box every time you do a law of sines problem. It's really, really important. So here we are at this problem. I've labeled it. I've drawn angle C. Remember, I always start with the angle, then side C is opposite it, and then the other side is next to it. So I've got things in the right place. The question I have is side C long enough? So what we do is we drop the altitude, that's called H, and we're going to go ahead and check that H. So I know the sine of 50 equals H over the hypotenuse 2. That's using that right triangle. So 2 sine of 50 is equal to H. And that is 1.53 is equal to H. But that means H is bigger than C equal to 1. So that means the C is too short to even reach the other side. Therefore, no triangle is formed. Okay? C is not big enough to reach the other side. So therefore, we don't have a triangle. Okay? The only other thing that would happen is C and H are equal, and that would mean you'd have a right triangle. So then you could just use Pythagorean theorem to find the missing side and complementary angles to find the missing angle. So that's it. That's how you do law of sines. You are now free to do some problems. Now, we are going to do some applications of law of sines, but those applications we will do after we do law of cosines. So most of the time you're just going to be given angles like this. The biggest application of law of sines and law of cosines, these are actually there are two big ones. The first one is navigation. In like World War II and World War I, they always had the navigator. The two smartest people on a plane were the navigator and the pilot. The navigator, because they had to figure out where it was going, all right, and the pilot had to get you there. And they had to communicate very closely, and the navigator would use trigonometry, just like this, to be able to figure out if they're going in the right direction. And that would be on airplanes or boats, submarines, etc. The other big application of this is surveying. And surveyors today use trigonometry all the time, except that now most of it is handled by software. So is most of navigation as well. And so software, essentially really good calculators, can find all this stuff for people pretty easily in programming. But in the old days, if you knew trig, you could automatically get these jobs. Alrighty? And pilots and captains knew navigation, so you could move up in rank as well. So that was always a good thing. Alrighty, that's all I have for you today. Good luck. Do some practice problems and really learn how to do this thing where you check, is it big enough, is it not big enough, etc. And that will help you. Alrighty, talk to you later. Bye. Whoops, pardon me.